I have a thing called the here actually is, and he was my teacher. So I learned quite a lot from him and I keep learning. It's really my pleasure to introduce you here actually. So I'm really honored. And he's going to talk about light coherence and things like it, correlations and quantum mechanics.
Thank you. Well, my thanks to Ravindran and the Institute for giving me an opportunity to spend these 10 days. I have come with the alleged interest of starting some collaborative work with him and his very energetic students. But at the moment, it remains at the stage of intention, but hopefully we will convert it into some practical work very soon. So this colloquium that on light coherence and quantum mechanics, it essentially grew out of a course on quantum field theory, rather field theory, that I taught in Hyderabad. Our institute there is very unusual. It's called the Tata Center for Interdisciplinary Sciences. So we have biologists, chemists, fluid mechanics, etc. So clearly the kind of field theory that I would have taught here to our high energy physics youngsters would be totally out of place there. And what I did instead was to collect interesting results from field theory in different areas and present it to them without the technical complications or derivations. And one was, of course, things from quantum optics. And then I thought that maybe this should be developed into a talk aimed at predominantly a student audience. So now I see in this audience, not everybody is a student, so I seek their forgiveness if I am telling things that you have known all your life. But for the students, I hope that you will find some new viewpoints which will take your understanding further, not only about light, but also about quantum mechanics. So I use the word coherence and correlations somewhat interchangeably. So let me begin with what exactly we mean by this. And then somebody pointed out that, well, this is a very good subject to talk about to students because this is the International Year of Light, whatever that means. So I dedicate this seminar to the International Year of Light. And of course, lead kindly light amid the encircling gloom. Gloom is certainly encircling us from all sides. So I hope that this will also be an invocation to take us to better times. So what are correlations and coherence? The crux of this matter is very simple, and it is that the average of a product is not always equal to the product of the average. Stated that way, you would immediately be shooed off the stage saying, what is this, are you taking us back to primary school? Well, let's see. So if you take a single random variable, then this, for example, the average of the square of the variable is not the square of the average, and that difference is called the variance. And if I take two random variables, then the average of the product is in general not equal to the product of their average. And in fact, that difference tells us how they are correlated. If they're uncorrelated, or in other words, they're independent, then that is 0. And if they are correlated, they're not independent, then it is non-zero. Now this can be applied to any random variable. And in particular, you can apply it to various physical quantities of interest. And in this talk, we would like to see the implications of such concepts for the light field. The light field treated both classically and quantum mechanically. And in that context, these correlations are also a measure of what is sometimes called degree of coherence. Coherence intuitively has a very clear meaning, but sometimes its technical meaning can be, quite opposite of what your intuition might tell. And I'll try to give you one or two examples of that. And there are obviously a measure of degree of fluctuations too. And one very beautiful and widely known manifestation of coherence is, of course, interference. And here is a beautiful picture of water waves interfering. And now we want to understand this notion of interference, not for water waves, but for electromagnetic field. And the classic experiment is the so-called Young's double slit experiment. And that arrangement is very simple. Here you have a screen, you have a small aperture, you shine it from the light left, and you take another screen, make two apertures, and keep this distance sufficiently large. And we will explain why it has to be sufficiently large. And then if everything goes right, if your light is reasonably monochromatic, etc., then you see these bands of bright and dark spots. This is what Young did many, many years ago. And in my opinion, this experiment is one of the deepest experiments in all of physics. We have all kinds of beautiful experiments, but Young's double slit experiment will be an all-time favorite. Its impact on classical physics is already known to be mind-boggling. With the advent of quantum mechanics, many things that enjoyed a very special position in classical physics got relegated to the dustbin. But this experiment, on the other hand, instead of being delegated to the dustbin, it became all important. In fact, it got elevated to a highly exalted position even in quantum theory. And this experiment may be the right way to actually teach quantum mechanics now. So what is this Young's double slit experiment? Now, as I said, this experiment was done long ago. And at that time, very little was known about the nature of matter, nature of light. Hardly anything was known. And therefore, in hindsight, it is rather remarkable that Young was able to successfully carry out this experiment. And in fact, when we were undergraduate students, we had to do this experiment. And we know how extraordinarily difficult this experiment is. You barely can see those fringes, and you have to do a lot of monkeying around. And it is far from trivial to actually see that pattern with what is called a good visibility. And all those things obviously are the reasons why this experiment is hard to perform and why it is so remarkable that Young could actually do this. Now, of course, since Young, there have been hundreds of textbooks, and this experiment has been presented in almost every textbook on optics. And the usual presentations in textbooks are idealized. They have to be, otherwise they are not textbooks. And with all idealized presentations, numerous subtleties, which are very realistic, very practical, and with their own deep physical nuances, are left out. And the description of Young's double slit experiment is no exception. So in the textbooks, what is done is that one considers a single incident wave with definite frequency and phase, and without any intensity fluctuations. And then you derive that formula, and you say, okay, look, this is what Young saw, this is what you should be seeing, and that's it. But in reality, sources of light are anything but simple. And as I said, Young didn't even know what was really radiating. What were the sources of light? Nobody knew of atoms at the time. And today we know that the sources of light are very, very large number of atoms. This number is of the order of Avogadro's number, which I don't know how many of us can count. We can't. And these large number of emitters, from the atomic theory, we know that they are in various states of excitation and de-excitation, and in the transition from an excited state to a lower excited state, they emit light, and the nature of the light that comes depends on all these dynamical details. And therefore, the light that comes out is not something that can be characterized by a single frequency, definite phase, or definite amplitude. And the light field we work with, whether it is this light that is falling on this floor or the light that we use in an optics lab, is a sum of sorts. I will put the word sorts of these large number of individual contributions. Okay? Since this number is so large, and we cannot really keep track of the mechanism of light emission very carefully, just as we do in statistical mechanics, to a very high accuracy, we can treat them as random variables, where the amplitudes, phases, frequencies will all be fluctuating. Then again, we go back to the question, if all these things are fluctuating like this, how did Young manage to successfully carry out this experiment? So that's a question we will ask, and we'll keep it in the back of our mind. Before I proceed, I want to introduce some simplifications. And one such simplification is so-called Gabor construction for the intensity. The intensity is a very good observable. Okay? And what is intensity? Intensity is basically the square of the electric field, but the electric field is rapidly fluctuating in time. In addition to all these fluctuations that I talked about, due to large number of sources, even if I look at light coming from a single source, its time variation is extraordinarily rapid. If you take visible light, then this oscillates about 10 to the 15 cycles, 10 to the 15 per second, which is very, very rapid variation. And you hardly can have detectors that can keep track of such rapid variation. Therefore, what we do is measure something which is the time average of that. And the time average is the intensity. So what do you have to do? You have to take some time-dependent signal, square it, do the time average, etc. But Gabor found that we keep doing this again and again, so we might as well do it once and for all. And he introduced this notion of a complex amplitude. So you write to your electric field, which is of course real, as a sum of a term of the type e to the minus I omega t, another of e to the I omega t. The first one is called the positive frequency part, other one is called the negative frequency part. And then the time average in intensity, you don't have to do any more averages. You simply multiply a positive frequency part with a negative frequency part. So it cuts down the complexity of the calculation, or at least it gets rid of a certain nuisanceable step which you have to do everything. And therefore, the time average intensity looks like E minus into E plus, or you can write it as E plus into E minus, because in classical theory, these are all commuting variables and it doesn't matter. But we'll see when you go to quantum theory that this order is very important, and the difference in various orderings actually leads to some very striking physical consequences. So now we come to the double slit. So again, in order to be able to appreciate all the nuances due to all these fluctuations of the amplitudes, phases, and frequencies, first let's do this for the ideal case. So in the ideal case, I have two sources whose amplitudes are not fluctuating. We'll call them alpha, beta. Phases are also not fluctuating. And RA, RB are the location of the sources. And R is the field point P. And it is a standard exercise to write down the amplitude at this point in this form. Now, when the field point P is very far from the slits, you can approximate these denominators by some constant distance L, but it will not be correct to do that approximation in the exponent, because as we all know, even a small change here can change the relative phase of these two terms, and that can have a very big effect. Therefore, we will make that approximation only for this amplitude part, and in the phase we will leave it as it is. And so this, to a very good approximation, is the amplitude due to these two sources. They are their phases, and you simply square to get the intensity. And the intensity, very elementary formula, looks like the intensity due to the first source, second source, and this term which is called the interference. Now, when the phase difference between the two sources is random, this term oscillates between -1 and +1 and averages out to 0, and you get the result that the intensity is just the sum of the intensities of the two sources, which is nothing surprising, that if you take uncorrelated sources, the intensity here, let's say on the floor, is just the sum of intensity from one source and the intensity from the other. And in the photon picture, even though I've not talked about quantum mechanics yet, we can straight away try to see what happens in the photon picture. This is simply interpreted by saying that the number of photons I receive at this point is just the addition of the photons coming from uncorrelated sources. That's it. But when delta phi is not random, then as you move the field point, this cosine will go from -1 to +1, and the intensity will show a modulation starting with some minimum value to a maximum value, and that is your intensity interference pattern. So this is that thing here. And a figure of merit is the so-called visibility, which if you are a photographer will immediately recognize as nothing but the contrast. The contrast tells us at the minimum how dark it is compared to the maximum, and that is the formula. And if the two sources are of identical intensity, then this visibility can take its maximum value of 1, otherwise it is always less than 1. Now this was an idealized situation. Alpha, beta, phi were not fluctuating. And now that we've understood the ideal case, let us go back and reinstate all the complications and see what we get. Now, as I said, we really have to take an ensemble average over all these light sources, which are an ensemble of emitters. And each emitter will have its phase, amplitude, and frequency. So we can think of a light source as a source with probability distributions for frequencies, phases, and amplitudes. And then, since you know the probability distribution, you can find out various statistical quantities like average, variance, of whatever physical quantities of interest that are to you. So now, in this case, without these fluctuations, alpha squared was just the intensity due to the source A. But now alpha is a random variable. Therefore, alpha squared doesn't have one value, and I have to evaluate this alpha square, the average of it in the probability distribution for alpha, and that is the intensity due to source 1. And note that in taking alpha square, I've already taken care of this very rapid, averaging over this very, very rapid time scale variations. So now this has taken everything into account. You go back to that earlier formula. These two cause no problem, but that interference term now involves alpha beta star, which is now I have to use the joint distribution for alpha and beta and compute this average. But unfortunately, that average has no simple relationship to the intensities of the two sources. However, you can use things like Schwartz inequality and conclude that whatever it is, it has to be less than square root IA IB. So you normalize it and call it gamma 1. And this gamma 1 is less than 1. So now the new interference formula, taking into account all these complications, looks like intensity due to source 1, intensity due to source 2, IA, IB, cosine times a gamma 1. And it looks very much like the ideal case, except that now I have a gamma 1 sticking around, which was not there. And I can compute the visibility now. Now you see that even when IA is equal to IB, the visibility cannot be 1. And in fact, the visibility of this is mod of gamma 1 times the ideal visibility. Ideal visibility is 1. Mod of gamma 1 is less than 1. Therefore, in general, the visibility is less than 1. You will not get perfect visibility anymore. And this is called first order mutual coherence function. And it's a property of the source alone, because what it really encodes is this correlation function of the amplitudes coming from 2 points on the source. So this is an intrinsic property of the source. And in fact, what you're really measuring in any intensity experiment are some intrinsic properties of light sources. And this, is an explicit way of understanding that.
So you go back to new ideal when the coherence between them goes to 0.
Pardon?
So when the correlation between them goes to 0, you come back to the ideal situation.
But no, when they're perfectly correlated, you go back to the ideal situation. They have to be perfectly correlated, not zero correlated. See, if they're uncorrelated, then alpha beta star becomes 0.
Oh, yeah, right.
Okay.
So when they're perfectly correlated, you get back square root of I.
That's right.
The information of the phases is inside alpha and beta, right? The information of the phases is inside alpha beta, right?
Definition of?
Information of the phases.
Huh.
I mean, the phases that you had in the ideal situation, the phi A, phi B, that's inside.
See, alpha is the amplitude, okay, and you can dump phases also into that.
So this, just want to clarify if the phase fluctuations, where do the phase fluctuations lie in this?
See, there is a phase here, okay. So what you can do at the moment, you can go stage by stage. You can say the amplitudes are fluctuating and the phases are not, okay. But then the separation into amplitude and phase is itself a little bit ambiguous, okay. So you will have to do this carefully. And if the phases are also fluctuating, amplitudes are also fluctuating, then you will have to also average this term here, okay. Now what did I do? I introduced a correlation function between alpha and beta star, and that is nothing but the correlation between the amplitude of one point on the source to another point on the source. But there is no reason to restrict the meaning of a correlation function like that, only to points on the source. And in general, at any point R1 and R2, if I now look at the electric field, E minus and E plus here, I can look at their correlation function and call that the correlation function gamma. When R1 and R2 are on the source, this gets related to what I already wrote. But if they're not on the source, but let's say they're in the field, these nevertheless have some meaning. So now let us introduce this generalized coherence function. And the important property of this is that since the electric field satisfies a wave equation, this function also satisfies a wave equation. Again, to keep the presentation simple and straightforward, let's assume monochromatic sources. Then this gamma will obey a wave equation like this. And it's a little bit curious because on one hand this gamma occurs intensity, which is somewhat particle-like, and yet it obeys a wave equation. The fact that it obeys a wave equation will have a very important consequence, which I'll come to in just a moment. So this is now the summary of the Young's double slit experiment, and this is what you find in textbooks. Now let us answer why we needed to keep that screen with two slits as far away as possible from the screen with a single aperture. If you have done this experiment, you will see that this is very important. Because if you keep it too close, then you see that the pattern is not exactly what you want. And if you keep it very far away, then everything is so dim that you don't see anything. Okay, so there is some interplay between visibility and brightness. And that is controlled by this requirement that that distance be optimal. So why? Why should we keep that far enough? And this is a very beautiful concept in optics, and this is called coherence due to propagation. In essence, what it says is that you can start with a completely incoherent source, meaning, for example, that alpha beta star correlation function vanishes when alpha and beta star are even a little bit away from each other. Then the source is highly incoherent. But even with such a source, if you go far away from the source and do an interference experiment, you have a good chance of observing beautiful interference patterns. So it's as if that light has acquired coherence due to propagation. And this is what it is called, coherence due propagation. And this goes by the name of Zernicke theorem. And intuitively, it's very clear that even if I start from a source which is very far away, and when it has traveled a lot, by the time it hits the screen, the wavefront is almost a plane wave, like a plane wave, and that is what we associate with a coherent source. But how do we understand that? This is too heuristic a proof, and the proof comes from a very simple application of something that we all learned, namely the Green's theorem. Now we have two objects here. One is the gamma function which I introduced, which obeys a wave equation. It obeys a homogeneous wave equation. But for every wave equation, I can introduce a Green's function, which is like an inhomogeneous wave equation with a source term. And when you have two quantities obeying the same wave equation, then you can use the Green's theorem. Okay? And if you use the Green's theorem, then you can show that this gamma for arbitrary points r prime can be written as a double integral over the source of a gamma restricted only to the source times these Green's functions, which are also what are called propagators sometimes. Now you see what happens. Suppose this is almost a delta function, that when s is even a little bit away from s prime, it is 0. But there's no reason why gamma has to be 0 even when r and r prime are very, very far apart. So an incoherent source, upon propagation, has given rise to coherence. And this is the basis of that requirement in the Young's double slit experiment. In fact, this is a very nice experiment you can make students do. You make them increase this distance between that screen with a single aperture and the screen with a double aperture, increase it, and measure the visibility of the interference pattern. And you will find that with increasing distance, the visibility will increase, but the thing will become dimmer because intensity falls. and you can actually quantitatively test this Fonsetat-Zernike theorem with this simple laboratory experiment. Okay. This is all very good. This is pure science, as they call. But now the call of the society is that what use is your science? And therefore, we should try and find some use for this. And geniuses like Michelson, they don't even have to think very much, and they can find uses right away. And not so genius ones will think a lot and still be unable to find any use for their scientific work. Now the point is the following. You set up essentially your double slit interference, and now instead of one source, let's say, I take two sources which, let's say, are half a wavelength apart. Then what happens is that where the maximum of the interference pattern of one, now the minimum of the other will be there, and therefore the intensity variation gets smoothed out. Visibility becomes zero. So this means that with extended sources, the visibility of the interference pattern can get substantially modified. So Michelson cleverly turned this on its head and said, let us use the way the intensity pattern, the visibility gets modified, and try to learn about how extended the source is from that. And in fact, what he did was he pointed this interferometer towards a star, and stars are point-like. Even if you go to the world's biggest telescope, star still looks point-like. This was a great disappointment to me when I went in California to one of the biggest optical telescopes, and I thought I would see the star to look not quite like moon, but at least like Venus, but the star still looked point-like. And of course, if you work out the angular diameter of the stars and what a telescope can do, this is not surprising. But so you don't measure diameters of stars by actually trying to see their angular diameter. It's hopeless. But Michelson had the genius of measuring this angular diameter in units which use the wavelength of light, which is very small. Okay? So what he did was that if you look at a star now, and the angular diameter of the star makes it look like an extended object, so the interference pattern will get wiped out beyond a certain region. And the extent of that region where the interference is non-vanishing is exactly a measure of the angular size of the source. You can make it all mathematical now. You can derive the exact formula. So this way he was able to measure for the first time angular diameters of stars, which till then was considered to be just a totally hopeless task. But there was a problem with this method, and I'll come to that. What is the problem? Problem is the following. You go back to this star and us, we are not separated by vacuum. We are separated by interstellar medium. There's all kinds of junk in it, and they severely affect the light. And in particular, they dephase these beams. So they introduce random phase difference between this beam and that beam, and therefore the intensity pattern gets completely wiped out. You don't even see this central part when the stars are more than a certain distance away. So the Michelson stellar interferometer, even though it's a beautiful idea, had limited applicability because for very distant stars or reasonably distant stars, it just wouldn't work because of this atmospheric distortion of the light field. And Michelson, in fact, managed to determine stellar sizes of only about half a dozen sources. And we clearly have many, many more sources than that. So, is this the end of the story? In science, there is never an end of the story. And an incredible remedy was proposed by Hanbury Brown and Twiss. Hanbury Brown is one name. Okay? you can ignore it, but some people may get thrilled that some connection to India of great ideas in science is sort of nice. So here the connection is that both of them were born in India. They didn't study in India, but they were born here. So there is Hanbury, Brown, a frequent visitor to India and a great pal of Radhakrishnan, who was the director of Raman Research Institute. They developed their friendship over countless amount of beer in Australia, I was told. So what is it that he proposed? He said interferometry need not be only between amplitudes, and it need not only be due to phases. And he said that intensities can interfere. That sounded very strange, because we saw that if I take two different sources, uncorrelated, intensities just add up, and even from the photon picture it meant you just count photons like you count peanuts, and then they just add up. And how can there be any modulation in intensity? That was the fundamental question. Not only is this a mind-boggling idea, it works even for uncorrelated sources. In fact, that's why it's a good alternative to Michelson interferometer, because even if the atmosphere is so turbid that it completely decorrelates the sources, this method still works. And with this, they went on to measure diameters of many sources. But I'll come to that in a moment. HBT, as being radio astronomers, they had done this with radio waves, radio astronomy. And they measured the sizes of many radio sources. Nobody questioned them at the time. And, particle physicists hardly pay any attention to radio astronomers, and they don't even pay attention to radios. Okay, so they're in their own world. So they said, these radio astronomers, they've done something. They put these huge disks, and apparently they measured the diameter of some radio source. Yeah, okay. How is this going to help me with my CP violation problem? Okay, don't do it. They later tried to say, we will do it with light. And then all the particle physicists woke up and said, light, photons, that's a particle, and, that's our property. And how dare these radio astronomers say all kinds of junk about something so beloved to us? And they started attacking Hanbury, Brown, and Twist. I'll come to that story in a moment. So why was the radio work uncontroversial? The point is, you can give a perfectly classical wave theory explanation of what they proposed. And let's do that. So now, instead of no chalk here, have you become so modern? Okay, yeah, good. So instead of two-slit experiment where the field point was only one, now I take two sources and look at two field points. Okay? So what do I have to do? I have to calculate first the amplitude at first field point due to source 1, source 2. Now, to show you the beauty of this, let me not modify it by introducing amplitude, phase, frequency fluctuations. We will keep them. We will keep the amplitudes and frequencies as unfluctuating. Then this is from the first one, this is from the second one, this is the frequency, these are the amplitudes, and this is the phases. If you want, you can remove a part of the phase here and put it into this. Answer to one of the questions, doesn't really matter. Likewise for A2, nothing. So now let me calculate the intensity at point 1, that is, square it. Alpha square, beta square, alpha beta square, blah, blah. Intensity at 2, alpha square, beta square, this, that. Now let the two sources be totally phase uncorrelated. That means their phase difference is completely random. Our two slits are uncorrelated sources. Then what happens? This averages to 0, this averages to 0, this averages to 0, that averages to 0. So the intensity at field point 1 is sum of the two intensities from the two sources. So also 2. And that takes back to our traditional wisdom that uncorrelated sources, intensities add. You want to view it from the photon point of view. Photons are just adding up like particles. No surprise. But now let's do something slightly more sophisticated. Let us look at the correlation between I1 and I2. What does that mean? That means I calculate the average of the product of I1 and I2 and compare it to the product of the average of I1 and I2. In this, it's an elementary thing to do. When I multiply I1 and I2, delta phi multiplying by delta phi gives 2 delta phi. If delta phi is random, that goes to 0. Likewise for that and that. But these cross terms, delta phi exactly cancels minus delta phi. So even if delta phi were random, this doesn't go to 0. It's as simple as that. That means that in the intensity correlation, even uncorrelated sources can lead to modulation in the pattern. Okay? And that is really the essence of the Hanbury twist effect expressed in wave language. So here is my calculation. Very simple. Again, you get some cosine modulation. Those things are unimportant. And here also you can introduce a visibility function. You can compute it. And one of the surprising results, which is elementary to establish here, is this nu2 is bounded by half. It can never go beyond half in this classical wave theory analysis. So for later convenience, let's normalize it. So we take the average of the product and divide it by the product of the average. If this is 1, then they're uncorrelated. If it is different than 1, then this is in general correlated. If you take equal intensity, the maximum value of this is 3/2. So what is the HBT intensity interferometer? Just as in the case of, so now G2 is called the second order coherence function. So here too you will see an intensity interference pattern, but now for the intensities, and when you go beyond a certain distance, this gets wiped out. So there's a certain region where this is non-vanishing, where the visibility, the second order visibility is non-vanishing, and that gives information about the extent of the source. So you can measure the sizes of various sources.
Haridass, one question. When you do the intensity correlation, you are measuring intensity at two different points. So let's say I count photons at one place and photons at another place. What do I average over? How do I average it?
So it's simple. Suppose I have one detector here, and I have another detector here. I'm measuring intensity here, measuring intensity. Simply multiply. In elementary computer, you multiply them and average the product.
Average over what?
Average of the product of intensities.
Time average, right? Successive missions, right?
No, you need not introduce time. You simply can think of it as a sequence of data.
Yeah.
So I have 1 here and 2 here.
Yeah.
N number of photons and
You get 1 here and 2 there, the product of some work is 2. And next time it is 3 and 4, and with even more work it is 12. And you keep on averaging, 2 plus 12.
several runs.
Huh?
You have several runs.
Yeah. Several runs.
And then you average over the runs.
Right.
That's what you go back to as ensemble averaging. That's the ensemble averaging in some sense.
Which one?
The ensemble averaging.
Yeah, if you now introduce all those other complications, then the treatment is more complicated, but the essence is the same.
If I'm watching the stars, how many days will the averaging go on? I'm not following this. I understand theoretically what you are averaging calculation.
Yeah.
Observationally,
Oh.
I am watching this. I am watching some sequence of N1, N2, N3, etc.
Yeah.
over a
Right.
period of some many minutes, hours, whatever it is. That's what I do, and then average over that period.
So what they did was that set up two detectors, two dishes, okay, and they watch some distant source, and you keep on receiving light signals on both of them. You just multiply average.
Average over the observation time.
But you need timing, right? You need to multiply at the same time. You need timing. For the two antennas, you need to do it at the same time. You need timing.
Well, the story is slightly more complicated. There are many variants of Hanbury twists. You can, for example, at the same time, at different points, do this correlation, or at the same place at different times, or mixtures of these things, and they give rise to different correlation functions. But that is simply, making it more involved. But
No,
basic,
if you don't keep time, then you will wash out everything, right?
not necessary,
No?
right?
There are
Because
two different points.
there are two different points.
If you don't keep time, seems like you will completely average it.
No, you see, if I take two detectors here, there is a time of observation, right? So you don't take one today and another 3 years,
So what
3 years
that's
later.
telling you? Yeah, you need timing. That you need to correlate with time.
I don't understand the question actually.
You think, how do you
So how-
ensure that you take the data at the same time in both detectors?
This is all some, experimental technology which,
So they take care of it.
yeah, therefore you have to do it in such a way that essentially some correlations are not lost.
Okay.
Okay.
Then the window is probably something.
Does the result depend on how long you observe?
Hmm?
How long, or what period you observe?
What period to observe?
We are averaging over something. So what is the observation time? 1 day, 3 days, 3 minutes? I mean, does it have
I think that depends on the accuracy that you want. You have to average over sufficiently large number that statistical errors, etc., have to be.
slots in there?
Depend on how intense the course is and how far you
Okay.
Time slots that
Okay, now let's come back here. So unless the Michelson case, random distortions don't matter now, because even if the phase difference is random, totally random, you still get this pattern. And therefore, wave theory is actually compatible with intensity interferometry. There is no big deal about it. And they did it, as I said, with radio waves first. I shouldn't say radio waves, because this already shows I am a particle physicist. They did it with radio sources and radio telescopes. And there was absolutely no controversy. And then they said, look, Michelson stellar interferometry didn't go very far. Why don't we use this method for optical sources? Hanbury, Brown, and Twist saw no essential difference between radio and light, which particle physicists, it should be their second nature not to make a distinction between these two, but they did, because they thought that radios are waves and light are photons. So when they proposed it, they run into huge opposition essentially from the theoretical physics community. And the objections was that this would not be compatible with the photon aspect, because photon aspect means number of photons should just add up, intensity should just add up, and there should be no modulation. And in fact, some people went so far to say that if this really worked, then we'll have to revise our quantum mechanics. Our whole idea of photons would be wrong, and there may be some major revision required, and therefore this is unlikely to succeed. And this kind of objection didn't come from, Janata of physics community, but it came from the cream of cream. The objection seemed to stem from a very specific sentence in Dirac's book. Now, Dirac is a great man, and he never uses vague words, and whatever he says has a very clear operational meaning. Okay. And in fact, I am always fond of pointing out that in his entire book on quantum mechanics, he doesn't utter the word tunneling even once, whereas tunneling was considered the hallmark of quantum theory. Now, why is it that did Dirac not know about tunneling? Of course he knew. But he had a deep philosophical viewpoint on how quantum mechanics should be viewed, and he didn't want to muddy it by introducing a concept of like tunneling, which depends only on one representation, namely the coordinate representation. So what is this sentence in Dirac's book? In case you guys think that I'm making it up, please go to your library, and I hope our library is still fortunate to keep some of Dirac's books, because as I've been traveling, I'm finding that first the 4th edition disappears, then the 3rd edition disappears, 2nd edition, and in some places 1st edition. Then you get some cheap Indian edition where there are all kinds of misprints and numbers are wrong, etc. So go to at least the 3rd edition, you'll definitely find it. Page 9, section 3. What does he say? He says, each photon then interferes with itself. Now already this, is a bad terminology, interfering with itself. I mean, what we really mean is that photon has several probability amplitudes and they interfere. Okay. It is not that the photon is running around trying to mate with itself. It's not interference of that kind. Okay, we will forgive this abuse of language. Interference between different photons never occurs. Never is a very strong word. Of course, here he didn't qualify what he means by between different photons. Presumably he meant photons from uncorrelated sources. Therefore, according to this Hanbury proposal would be in direct violation of this. Unfortunately, Dirac he didn't say anything about this, even though he was alive. But other people were very influenced by this. And when Hanbury gave a talk, Feynman is supposed to have been, Feynman, a very energetic guy, jumping up and down, and, he said, no, this is all nonsense, it can never work, and so on. But Feynman is a smart guy. He recovers quickly from mistakes. And around midnight, he's supposed to have called Hanbury Brown and said, yeah, it can happen. He didn't say you're right. He said it can happen. So that's it. This was the objection. And this objection had a very big impact, actually. But let us see. If the Hanbury-Brown effect is there, does it mean the end of the photons? Do we require dramatic modification of quantum mechanics? Now, this is the experimental setup for measuring the Hanbury-Brown effect. In the laboratory, you can simply split it in any way and measure the, intensity correlations, etc. So now I want to look at it from the point of view of quantum theory. Please allow me a few extra minutes than what I'm entitled to. An excellent reference for all this is Fundamentals of Quantum Optics by Clowder and Sudarshan. And in fact, the whole area of quantum optics started essentially with the discovery of the Hanbury-Brown twist effect, and in particular, how to understand it from quantum mechanical principles. And people like Glauber and Sudarshan, and they made major contributions, and a totally new area of science was born. And this book is delightfully inspiring, and it's also very interesting that they actually do calculations even to the last step. So even very junior students can read this book and learn, and everything that I said about Farnsted, Zernike theorem is all beautifully derived there. So please get a copy of this and read it. So now when you go from classical to quantum theory, the source in classical theory is now replaced by some state of the electromagnetic field. Okay? So this is a quantum state of the electromagnetic field. And this state, as we all know from quantum mechanics, can be a pure state or a mixed state. I will not go into too many of those details. And the intensity measurement is now viewed as a quantum process. In particular, as the probability of absorption of photons by some detector. And that will be the intensity measurement. And that probability is given by the average in the quantum mechanical state. Now electric field becomes an operator. So the positive frequency part and negative frequency parts are operators that do not commute. And therefore the order is very important. And otherwise it looks very much like our classical intensity formula. But now the meaning is extremely different. E plus is called the annihilation operator, E minus the creation operator, and now you can just do your calculations. Fortunately, the electromagnetic field is nothing but an infinite collection of harmonic oscillators. And harmonic oscillators is the first thing we learn in quantum mechanics. Therefore, if you have really understood your elementary quantum mechanics, you can do all these calculations. You have to be careful, of course. Order of the terms is important, etc., etc. So there is one particular order that is used called normal order. This doesn't refer to any psychological attribute. It is a phrase that was introduced in the early days of field theory, that it is an order which gives zero value when you evaluate it in the vacuum state. Because vacuum is supposed to have zero properties. Therefore, every observable put in the normal order form will have zero expectation value in the vacuum state. And in terms of our quantum mechanics, it means put all the creation operators to the left, all the annihilation operators to the right. That's what the normal order is. And now we can go through our double slit experiment quantum mechanically, and the gamma, which was the first order coherence, gets replaced by this quantum mechanical expectation value, normalized in this form. And if you look at the intensity formula, it looks exactly like the classical one, except that gamma 1 of classical theory is replaced by G Q of 1. Therefore, observationally, first order coherence cannot distinguish between classical and quantum theories. They take some value, gamma takes some value, G takes some value, that's all. There is no other deeper distinctions to be discovered. Okay, all this I will leave it now. Now let's come to Hanbury twist. This now I can interpret as two photon correlations. In other words, it's a situation where I have two field points, so I'm actually detecting two photons. So we have to calculate the probability of two photon detection, and the relevant expectation value is now 4. And so this is the object, and you have to normal order it. When you normal order it, the pluses, I think I have made a mistake here. There should be plus, so minus, minus, plus, plus. And you can evaluate it for whatever you want. Let's take a simple case where the state of the field is of a type Nm for some modes. Then it is elementary. Even our BSc quantum mechanics tells us that this is the Hanbury twist correlation, 1 plus cosine. And you see, if the sources are one photon sources, that means if Nm are less than 2, then both these go away, and you're left with only that. And here, the minimum is at 0, maximum is at some finite value, so the visibility is 1. So the second order coherence function can, in the quantum mechanical case, have a generalized visibility of 1, whereas the classical wave theory at most gave half. So second order coherence immediately distinguishes between classical theory and quantum theory.
Sorry, that average is time average also. That average is time average also.
Which one? This one?
The top row.
The top one?
Yeah.
No, this is the average, this is the quantum mechanical expectation value.
And you have this function, the function of R1, R2, T1,
So you take some observable which can have R1, T1 dependencies, depending on your experimental setup, and then that is its expectation value in your quantum mechanical state is evaluated. Again, you can choose, the Heisenberg representation or Schrodinger representation, etc. There are no difference from standard quantum calculations.
The experiment is actually measuring intensities in two detectors, which is already the expectation of E minus E plus, right? So why is this the 4-point function? You must have a product of two 2-point functions, right?
The intensity.
Yeah.
It's a product of two intensities, and each intensity is E squared.
Yeah, but the intensity is already the ensemble average of E minus E plus. That's how you have defined it.
That's only for, in the first order coherence case. See, intensity operator is E squared. Okay?
But the moment you make a measurement, right?
No,
How are you making a correlation between two independent measurements, right?
no, first, see how many electric fields are needed in this correlation function. You want to take a product of two intensities. Each intensity is quadratic in E.
No, that is okay. No, I understand the theory. But
Yeah.
I'm saying the observation.
Yeah.
Not that I understand the...
So the observation I have to undo this. So I describe a detector in some way, and then write down the probability amplitude for the detector to absorb two photons.
So it is a different thing.
So once again, so there you will get two electric field operators.
Okay.
Okay, and then that's the amplitude. And then you must square it. So even from the actual setup of detectors, etc., you will get expectation value of 4 electric field operators. Okay, just very quickly, there are many variants of HBT correlations. For example, you can measure intensity at one time and intensity at a slightly shifted time and measure the correlations, etc. And they all have their own significance, but the underlying physics is the same. So now I think I'll only end with this because I don't have time to explain everything else. We will address the question, if the Hanbury-Brown experiment had been done with photons and worked the way they expected it, will there be any problem with the photon interpretation of quantum mechanics? And as soon as HBT effect got to be known, Purcell looked at it and he immediately realized that not only will this not be a threat to photon concept, it actually deepens our understanding of what photons are. Okay? And he says that this is actually not to the detriment of quantum mechanics, but it is to the extreme health of quantum mechanics if the HBT effect really works. So I will end by explaining to you what I call the Purcell criterion. Purcell criterion is, when will you see a non-trivial Hanbury-Brown twist correlation and when you don't. And even though you should do a proper quantum optics calculation, it suffices to simply restrict ourselves to a single harmonic oscillator and give a crude version of Purcell's argument. So we want intensity correlation. What is intensity? It's number of photons. So in a single harmonic oscillator, it's the number operator. So you want to find out the expectation value of n squared and compare it with square of expectation value of n. But since we want to be normal, this has to be a expectation value of the normal ordered product of n's. Therefore, I must put these guys. N is A dagger A. When you normal order it, A dagger A becomes A dagger AA. And then use the commutation relations of A dagger, and you can write everything in the end with n operators only, but the non-commutativity makes a difference. Simple calculation, here it is. A dagger A. So you get this extra guys sitting around. So G2 is expectation value of n square minus average value of n, and it always helps to add and subtract. Sometimes 0, sometimes 1. So here let's do it with 1. So I put minus 1 plus 1. When I put minus 1, this becomes n square minus square of n minus n. But what is this? This is the variance. And this is the difference between the variance and the mean. If this whole number becomes 0, then G2 is 1, and there is no Hanbury-Brown twist correlation. But when does the variance become the mean? When the statistics is Poissonian. Okay? So Purcell said if your photon source has photon number distribution which is Poissonian, there will be no HBT. If it is super Poissonian, namely if this number is more than 0, then you will get positive HBT. If it is sub-Poissonian, you will get less than that. Okay? That's it. Beautiful criterion, and it leads to some very surprising results. Photon number eigenstates. Photon number eigenstates, obviously, the expectation value of n squared is square of n. Therefore, it's sub-Poissonian. Okay? And therefore, you will see HBT, negative HBT. Here I want to point out a flaw which is repeated ad nauseum, and every time I hear it, I feel like scratching myself, because this is certain abuses of language and concepts are unbearable. And what is said is that in the limit of very large photon numbers, things become classical. Okay? Now this shows that that's not true. However large your n, if it's a photon number eigenstate, it does not show a classical-like behavior. There's an even simpler argument for that. You take a photon number eigenstate, expectation value of electric field, expectation value of magnetic field is exactly 0. But that's not what a classical electromagnetic wave is. So it's not true that large photon number means classicality. Of course, experts know this, but sometimes in talking about this quantum to classical transition, people take all kinds of liberties, and that should be put down right in the beginning. I'll give you one example. Photon, thermal source. We consider thermal source to be most incoherent because thermal agitations, nothing is correlated, etc. You compute this quantity, and you find that this is super Poissonian. So for a thermal source, actually there is a positive Hanbury-Brown twist correlation. Yet we think of thermal sources as incoherent. So that's why I mean that coherence and correlations, their precise synonymity has to be very carefully looked at. But look at the other end, coherent state, lasers. In lasers and coherent states in BEC, it is a Poisson distribution. And they are supposed to be highly coherent. But HBT is exactly 0 for them. Okay? So that's and in fact, Glauber says when he heard about HBT, he had an inkling that for lasers this has to be 0, and that's what set him to, according to him, thinking about this issue. So lastly, some data.
What was his reasoning to expect it to be 0? What was his reasoning to be expected to 0?
That time he doesn't say that, because it's a non-trivial result. So here is, for example, a thermal source, and you see a positive Hanbury-Brown. When you go to large time differences anyway, the effect gets washed out. You should only concentrate in this small region. And this is a thermal source. Very, very cold, 1.4 microkelvin. Okay? And still a striking positive Hanbury-Brown twist correlation. And we saw that thermal sources are super Poissonian and they must have positive HBT. Okay? And same thing. And here, look at this. This is for lasers. Okay? Flat. 0 HBT. And Bose-Einstein condensation. 0 HBT. Okay? And like that. Unfortunately, I had no time to tell you this, but Fano argued that what is really happening is Bose statistics of photons, which is what is giving rise to this effect. And if that is so, for fermions, you should expect negative HBT because they obey Fermi statistics. And I have no time to discuss all the details. And here is a striking experiment. For bosons, positive HBT, fermions, not as small, striking negative HBT. So this shows the correlation between statistics and HBT. Last point, this is completely universal. It has nothing to do with light, BEC, lasers, etc. As long as you look at particles in 3 spatial dimensions, there are either bosons or fermions. And we can look at other bosons, pions. So this means that there's an HBT even for pions. So you look at 2-pion interferometry in particle physics experiments. And just as the Hanbury-Brown experiment told us the size of the source, the 2-pion interferometry will tell me what is the size of the region from which the pions were emitted. And here is the experiment. Positive HBT correlation for pions. And I will stop here. Einstein said in a gender insensitive way, he who understands photons will have the last laugh. But now we are in the age of gender correctness. I will say he or she who understands photons will have the last laugh. And Hanbury, Brown, and Twist certainly deserve that laughter because they understood photons better than even some of the stalwarts of particle physics. Thank you.
Some of these experiments were being done in Mendel's lab when I was at Rochester.
Huh?
Some of these experiments were being done in Mendel's lab. That in fact, that later, for example, Steve Feinberg was a student doing their experiment.
I see.
And he of course had set up the experiment. He didn't know about Brian Twist. So we argued about it. He went to Mendel. Who is correct? The Mendel he understood.
Why didn't they see it in this micro, in the radio astronomy, all this